it's homework 15.
Okay.
And then, yeah, so, yeah, it's 25A. So it's one, there's a, you'll probably just want to look and, this is a diagram.
Okay. So, okay, we're back to looking at planes between, or angles between planes. So explain why, okay, we did, I think we did this last class, but I don't know if you saw the video on that. So here is a normal vector to that plane, and looks like another plane that's going to come. You know, really use your visualization skills there. So there's our second plane, and it's got a normal vector to there. So there's our normal vector to that. So we are talking about this angle. Alpha is here, and we're trying to compare that to another color, to this angle beta between the two planes. So our claim is that if you imagine, you know, coming along here and coming over there, we're going to create a quadrilateral, and that we know that these two are right angles. So we know that, so in a quadrilateral, it's like two triangles, so that sum of the angles in a quadrilateral is 360 degrees. Two of those are right angles, so that means alpha and this angle down here have 180 degrees left to share. So whatever this angle is over here is going to be 180 minus alpha. But if you look at beta right here and you extend that line there, you can see that this angle right there plus beta is 180 degrees. So that means that alpha and beta, wait a second. So that means that beta is equal to alpha, right?
Yeah, that was just our question.
That was the question.
Keep going, or? No, we got E.
Yeah.
No. That's just A. 35B.
Oh, it's where lines intersect planes.
Yeah, we just didn't know how to do that.
Okay, so 35B?
Yeah, because it's 37 the exact same.
Yeah, 37.
Yeah, so all we need is 35B.
Okay, keep
So,
coming.
explain why the line XYZ equals 8, 9, 10 plus T 3, 4, 5 is perpendicular to the plane 3x plus 4y plus 5z equals 10.
Yep.
We got that part. So then B was, where does the line intersect the plane? That's the one we
Where does this line, okay, we did this one, yesterday.
Yeah, we got that one. We just need to, we don't know how to find where it intersects the plane.
So what we want is, where does this intersect that plane?
Yes.
So if you look at the x here and the y and the z, we can kind of separate them out. So the x is going to be 8 plus 3t. You with me there?
It is what I thought it was.
And the y is going to be 9 plus 14. And the z will be 10 plus 5t. Now if we substitute these in for the x, y, z here, you'll have only one variable t to solve for. And once we know that, t will come back here and take this plus that number t times that, and that will be the point that's on this line, that's on that plane.
That's what we assumed it was, but we just didn't want to do all that work and have it
And have it be wrong.
Yeah, we're gonna do some weird voodoo math just to have it backfire.
Ah, yes. Okay. Is there another one?
This one's on homework 16.
Okay.
It's the weird theoretical stuff.
Yeah, looking at 5. number 6, it says true or false, and then it has a determinant, and it has A, B, C, D.
So is this going
Yeah.
across A, B, C, D?
Yes. Equals another determinant, and it has A minus KC.
A minus K, C.
Yeah, and then B minus KD, and then C and D. For every real number K.
Well, should we just evaluate each determinant and see if they are in fact always equal? So on the left, I'll do the one on the left, you do the one on the right. Okay, that line, A, D, minus B, C. Okay, so let's do the one on the right. So we're gonna have to multiply there and I'm gonna distribute. So that's gonna be, so I'm gonna say, is this equal? A, D minus, looks like an alphabet soup, K, C, D. Is that okay for multiplying those? Minus, B, C, I guess, minus, trying to kind of do it alphabetical, K, C, D. So that's going to be A, D minus K, C, D minus B, C plus K, C, D. How about that? It is indeed equal.
And what other one?
So here's what's really happening, because this is actually kind of like, down the road, if you take a linear algebra class, this is a big deal. Because what we're saying is that this determinant here is equal to, we would call this row a linear combination of these two rows. So we multiplied this row by K and subtracted it from that row and replaced that row by that, that's a big deal, but not for us in here. That's just interesting at this point.
And then for 11, it has in exercise 10, one row is a multiple of another row, and the value of the determinant is 0. Is this a coincidence just right? So we said no, it's not a coincidence,
Right.
but we don't know how to like
Explain it.
Yeah, we don't know how to say it.
But are they just doing a 2 by 2 or are they saying with any?
It's a 3 by 3.
It's a 3 by 3.
3 by 3.
Yeah, so the first 2 rows are multiples. Of
So the problem we just did was number 6. So I'm going to try to claim we can use that to prove this.
Okay.
So tell me what 11 looked like first.
10, so it's 1, 2, 3 on the top, and then 2, 4, 6, 17, 18, 19.
So what we said and it was kind of hard to tease all that out, but that last one said is that if you multiply a row by whatever number you want and add it to a second row, whatever we want, and replace that row by the sum, it doesn't change the value of the determinant. So the idea is when you see this, you could say we could multiply this row by -2, and it would become -2, -4, -6. Add that to this row and replace that row by that. But when we add this row to that row, we're going to get a row of zeros. Now, expand along this row. Evaluate this using expansion by minors. We're going to get 0 times its minor plus 0 times its minor plus 0 times its minor is going to equal 0. And that's true no matter what size determinant you have. So what it's saying is that if any row or column is a linear combination, we say, certainly if it's a multiple of another row, then the determinant is 0. And that's a big deal too, but not in what we're going to do.
Yeah, we knew that it wasn't a coincidence.
Yeah.
We just couldn't say it in a way that sounded smart.
We're like, we don't want to sound.
Fair enough. Fair enough. Okay, so let's go on and do some more applications of determinants. So this is more 12 and 8 applications of determinants. So we saw Kramer's rule at the end of last period, which is interesting but not terribly useful. I think this one's a little bit cooler, so we can talk about an area of a parallelogram. And this is going to be like in 2 dimensions. And then we'll expand that that to a three-dimensional idea, which is kind of crazy. So it turns out that if you say V1, one vector is going to be, we'll just say A sub 1, B sub 1. And a second vector is going to be A sub 2, comma, B sub 2. So there's two vectors. We put them in standard position as we put them so that they're both at the origin. And so you're going to have one vector, V1, whatever, going some way like this. A second vector, V2, is going to be over here. So any two vectors in a plane, so any two-dimensional vectors, will form a parallelogram. It turns out, crazily enough, that the determinant of the vector formed by, the value of the determinant formed by making the vectors into a determinant, either using these as, we would say, row vectors or as column vectors, either way. The absolute value of that determinant equals the area of that parallelogram, which is pretty remarkable. But you can kind of see it like what we were just talking about in the last question. In the event that these vectors were collinear, they were right on top of each other, then they would be multiples of each other, right? One would be a multiple of the other, which you just said meant that its determinant would be 0, which makes sense, at least geometrically, that if you're trying to talk about the parallelogram formed by something that has these as the two sides, it doesn't have any area, its area would be 0. So at any rate, what we're going to say is that this A1, B1, A2, B2. Now there's not a great way to write this. The absolute value of the determinant, I don't know what that is. That is going to be our area of the parallelogram. So in a sense, what you're getting from this determinant, somehow it's kind of measuring how far apart those vectors are, right? So if they're right on top of each other, you're going to get 0 for the determinant, not make any kind of area out of that. Take those vectors. Now, the biggest area you could get was if it would be a rectangle, and that was perpendicular. And so as you open that up a little bit, the determinant's going to get bigger and bigger and bigger. And the biggest it can be is if the two rows or two columns, however you want to visualize that, are actually perpendicular vectors with those given numbers there. An interesting idea. Let's do an example. So find the area. Find the area of, so I'm going to ask you to find the area of the triangle. We just talked about parallelograms. Of the triangle with vertices. P is going to be 1, 2. Q is going to be 3, 6. And R is going to be 6, 1. How about a strategy? What do you think? I agree. What kind of vectors should we look for? Which ones were you thinking?
I was thinking PQ and PR.
So that's the key, is you got to make them have the same initial point. It doesn't really matter if you go PQ, PR, RQ, RP, or whatever combination. So the idea is you have these 3 points, whatever they are, in the plane. And so if this is P and that's Q and that's R, so they are going to form a couple vectors. And we know that the determinant's going to find the area of that parallelogram. We want the area of the triangle. And so how will they be related? Whatever, just have. So we're going to make PQ, make PR, get a determinant, evaluate it, take the absolute value of it in the event that it turns out to be negative, and then take half of that. Make sense? All right. Colton, you trust yourself finding PQ anymore, or you don't trust your arithmetic any longer? So it's going to be
PQ.
PQ.
Oh, no, 2, 4.
2, 4. PR, what was PR? Did I write down? Oh, here's R. It's going to be 5. I lost it. It's going to be, that's the one that's like 1.
Negative.
5, negative 1. That'll make a difference. Okay, so we make a determinant out of it any way we like. Don't really goof that up. You can go rows, you can go columns. Evaluate that. Negative 2 minus the 20 from negative 22. Doesn't really make sense. The area could be a negative, so we'll take its absolute value. It's 22. That's the whole parallelogram. So the triangle, it's going to be 11. Isn't that kind of cool? So let's step up a dimension. What do you think? 3D. What's it going to look like in 3D? We're not talking area. Talking volume. It's not going to be the volume of a parallelogram. So now here you got to really visualize. So imagine you got one vector, another vector. Now these don't necessarily have to be perpendicular. It's not going to necessarily be a box. It might be a box that's like somebody leaned on and pushed over. So it might be, and I don't know how to draw a good one of these. Not that I could do this. So I don't know. It's going to be a, well, you're going to have to imagine. I don't think I can help you with that. Okay. So it's called a parallelopipe. Trying to expand your vocabulary every opportunity. So a box that's been leaned over. So now the sides are not necessarily rectangles, they're going to be parallelograms. That is called a parallelopipe. So the volume of a parallelopipe. Parallelopipe. Like it's a word that never ends. Okay, so 3 vectors in standard form. So that just means they're gonna, like we saw before, they're gonna share a vertex. Like you put them all at the origin. 3 vectors in standard form the sides of a parallelopipe. The volume of said parallelopipe is the absolute value of the determinant formed by making rows or columns of the vectors. That's crazy. So I actually have an example here that's pretty slick because it's actually a right parallelopipe. So it's not one of these that's been pushed over. It's actually going to truly be a box. So the vectors are actually going to be perpendicular to each other, which means we have the opportunity to find the volume here using our determinant, which I think you're going to like, and then we can also compare it to finding the volume the old-fashioned way, length times width times height, which we couldn't do if it wasn't a right parallelopipe. Does that make sense? All right, have at it. So we have A is 5, 1, negative 2. B is 0, 3, negative 1. And C, these are now points, 5, 2, 4. But we're going to make it into make them into vectors by going from the origin. So we're going to look at vectors OA, where O is the origin, OB, and OC. That makes sense? So in a sense, they're also the vectors. So the points are really the same as the vectors. So we're going to first do this using, so we're going to find the area using a determinant. And then we're going to confirm and hopefully find, or not area, volume. And then find the volume using length times width times height, the old-fashioned way. What are you thinking? Down, 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 minus up, minus up, minus up, or you want to go with the expansion by minors?
I was just gonna do the down.
That's
I
all
like
right.
the down thing.
I do too.
I like the down one unless it's more than 3. Then you get a new expansion.
You can have a choice anyway. Yep. I agree. I'm on board. What you doing now? Okay. Or is this new uncharted territory here?
A little bit, yeah.
Okay, so here's our 3. You see how I got the 3 by 3 determinant just from the rows.
Yeah, I got it.
Okay, and we have 2 different ways of evaluating a 3 by 3 determinant. One way is to recopy the first 2 columns. And now what I'm going to go is I'm going to go down and multiply those 3 entries together, plus down, plus down. Then I'm going to come back and go minus up, minus up, minus up. And that number is going to be that determinant. So I'm going to go 5 times 3 times 4. 5 times 4 is 20. 20 times 3 is 60.
Now subtract the grade.
No. The ones coming down are all added. The ones going up are going to be subtracted. So we're going to add, and then coming up, change colors. So going up, we're going to subtract. So 1, negative 1, 5 is a negative 5. And we get a 0 on the last one, that's a good break. Minus 10 times 3 is a negative 30. And then minus a negative 10. And we got a minus 0. So it looks like
You're thinking of expansion by minus.
No, I'm doing this one.
so 60, 30, and 10 is 100. Minus 5 is 95. Is that what you guys got?
Yes.
So that is our log. Crazy. Alec, did we get that?
No, I forgot. 0 times 4 is 0.
Yeah.
Hey, guess what we did the first couple.
Easy to do. We okay other than
Yeah.
the multiply by 0 issue? Okay, so now we're going to do length times width times height. So OA, OB, we're going to look at their magnitudes. And that's going to be length, width, and height. So the magnitude of OA is going to be what? So we get square root of 25 plus 1 plus 4. That's going to be 30, square root of 30. And the magnitude of OB, tell me if I'm going too fast. So it's going to be 0 plus 9 plus 1 square root of 10. And the magnitude of OC is square root of 25 plus 4 plus 16. Looks like square root of 45. That look okay? And should we call that 3 squared of 5, get the numbers a little bit smaller. So length times width times height is going to be the square root of 30 times the square root of 10 times the square root, 3 squared of 5. Let's see. So I'm going to think of that square root of 3 times square root of 10. That's the 30. Square root of 10, 3 square root of 5. Is this going to work? Did I do that right? 25. 4, 1, 30.
Yeah,
25, 4, 16. It's not gonna work, is it?
No, it can. You chucked it.
Something's not right. We got 10 times 3 is 30, square root of 15. Is it gonna work? What did I do wrong? Oh. Right, you see, like 5 equals 5. I can jump to 0. What did I get before I did this? Oh, I didn't get 95 before. What did I do wrong? 5, 1, negative 2, 0, 3, negative 1. 5, 2, 4, 5, 0, 5, 1, 3, 2. 20 times 3 is 60. Plus negative 5.
On your second down, it should be 5.
Which one? Here?
No, the 10 shouldn't be 10, should be 5 because it's 1, negative 1, 5.
No,
Wait, no, yeah.
I don't, what happened? Did we mess up one of the points?
What if I wrote it down? Well, shoot.
Well, obviously you messed up something visually equally.
Oh, I wrote down, when I did this originally, that was a 2, so I'm not gonna match mine, but these should still agree with each other. So, what did I do? 1, 3, 2, so 20 times 3 is 60, negative 5, 0. Oh, because if I do that, they aren't gonna be right anymore, so then they won't agree. This is supposed to have been a 2. Now, all credibility is destroyed. Should we fix it?
Oh, sure.
So let's see if we can just retrace our steps. That was my fault. So this should be a 2. So I'm going to make this be a 2. And so this is also going to be a 2 there. Okay? All right. Sorry, guys. Let's see what we can do now. So this, I'm going to go a little slower maybe. Let's see. 10 times 4 is 40. That's going to be 1, negative 1, 5 is a minus 5. That's still going to be 0. And 10 times negative 2 is negative 20, but it's a minus. Negative 20 makes it a plus 20. That's going to be minus the negative 10 is a plus 10. And that's going to be a 0. So let's see, we have 20, 30, 70, minus 30, 70. So what I got there? Hold on.
No, because when we, wait.
I write these down, still correct. 5, 1, negative 2. Should be 0.
Wait, did we put the points into the determinant rather than the vectors?
Well, the points are the vectors.
Oh, wait, yeah, because it's origin and determinant.
I still don't have it right. Yeah, it was a 2. Well, we're just going to stop. I mean, these aren't going to be equal because I wrote these down wrong, and so then it's not a right parallelopipe. And so without the correct values here, there's no way to make these be the same. So what we did here is write the volume. This isn't going to be correct because we can't use length times width times height if they're not right, not perpendicular. So.
Oh, yeah, because if you open the origin, there should have been a 0 in each of them, huh?
Not necessarily. Not necessarily.
Well, there's a 0 in one of them. No, never mind, I'm wrong.
Yeah.
So.
Okay. But do want to talk about is just get a jump on the next thing. I want to talk about cross product.
Cross product. We probably before cross product.
So that was a fail. let's do, so we're going to start on 12.9. And we won't finish it, but we'll get a start on it. So 12.9, determinants and vectors in 3D. Determinants and vectors in 3D. So we know that a vector in component form, say vector OP, which is given in component form by 3, 5, 6, can be written in IJK form as what?
3i, 5j.
Yeah. 3i plus 5j plus 6k. So we okay with that part?
Mm-hmm.
So what's really kind of cool now, we're going to use this whole idea of IJK notation to define a new operation, a new kind of multiplication of vectors. So we will use the IJK notation to define a new operation on vectors called the cross product. So it's crazy because it uses this idea of determinants and the IJK notation to create a whole new operation in between two vectors. So I'm going to destroy the evidence here so I have room to work with. So we're going to say if vector v is going to be v1, v2, v3, and vector w is going to be w1, w2, w3. Then we define v cross w, and we write this like with a big X, like you're back in elementary school when you first learn how to multiply, and you write 2 times 3 is this 2 big X times 3. So it's called v cross w, and it's going to be defined as this vector where you write IJK for the top row. And now order matters. So when you say v cross w, then v has to appear as that middle row. So that's going to be v1, v2, v3. And the w has to be w1, w2, w3. So order matters when you do the cross product of vectors. And so what you get then is you always expand along row 1. And you remember how we do this using expansion by minors, that there's a sign associated with these positions. And it goes plus, minus, plus. So you start positive in the row 1, column 1 entry, then you alternate signs. So what you get is I times its minor, which when you delete the row and the column that I sits in, it'll be v2, v3, w2, w3. v2, v3, w2, w3. Then expanding along that row, we're going to get a minus from the sign pattern, j. So it's always going to be a minus j, and then you delete the row in the column that j sits in, and that minor is v1, v3, w1, w3. And then you get a plus k, and you delete the row in the column it's in, and you get v1, v2, v1, v2, w1, w2. So what you get out of this, when you see, now, and then you evaluate these, but you're going to get a number times I, a number times j, a number times k. What you get is a vector. So when we did u dot v, the dot product, you took 2 vectors, and what you got was a number. When you do a cross product, what you get is a vector. And this vector, it turns out, has some pretty remarkable properties. Now, the first thing we can see, because the order matters, that if you switch the order, that W cross V, when you switch those rows, what does that do to the value of that determinant? It changes the sign. So it's going to be the negative of V crossed with W. I didn't get time enough to work an example, so we'll have to pick that up next time. But what we'll see, what's kind of amazing is that what this new vector does is it will be perpendicular to both of the originals. So you'll start with two vectors, and when you cross them, what you get is a vector perpendicular to both of them.
V cross W is perpendicular to V and W.
Yeah. So, and there's some other cool properties too. Well, that'll have to wait. Yeah, it'll be back to you guys again.